Sarah, do you want me to share screen or are you going to?
Sure. Why don't you do it for the intro slides and then I'll take it over.
Wait, sorry. Can you type in the chat? Okay, let's get started. Welcome everyone to day 3. We got a fun day for you here. Hopefully you'll start to see the last 2 days we were talking more about like how to program and designing programs. In the last 2 days we're going to talk about more about how do we make a package. So we have some exciting things in store for you. Just some announcements. No optional lectures today where we don't have any scheduled activities in the afternoons or expectations of you working on your project today. For the in-person participants, we have a workshop dinner at 6:30 at 5 and Dime. You can check out the details. It's a short 10-minute walk from Sierra in downtown Evanston. And we also have plenty of Discord channels to explore. So if you haven't explored the Discord channels, here are some that we thought could be of interest. As always, every day we'll remind you we have an anonymous feedback form. If provide us feedback as often as you want, and continuous stream of feedbacks throughout the workshop is appreciated. And then also a reminder yesterday showing you the vocab list. We have a kind of crowdsourced vocabulary list. So if you ever hear a bunch of jargon and you're not sure what it is, it might be on this list. If it's not on the list, you can help us contribute to it by adding it to the list so that future attendees will be able to reference it. And our standard, how do we ask questions? Please ask questions often. You can ask questions in the chat box on Piazza or on Discord, and we'll try to monitor all of these locations during the workshop. And just remind everyone the goals of the workshop. By the end of the workshop, you'll be able to use the language of software development, develop and release an open source software package, and write code that follows the best practices of software development. And then specifically for today, our goals will be to use docstrings and Sphinx to document code for others to use and to set up and release Python packages publicly. And then we don't have any specific project goals for you today. Hope you can take a little break from the intensity of the workshop so far. Yes. And then just a reminder, just in case, I don't think we made any changes since yesterday, but if you haven't been updated in the last few days, to remind you to do a git stash, a git pull, and a git stash pop to apply any changes from that we made to the GitHub or Code Astro GitHub repository. Okay, I think that's it for the intro slides. So Sarah, do you want to take it away with releasing code?
Yep. Can you hear me okay in person and online?
Yes.
All
Yes.
right. So yeah, I'm calling in remotely today. I'm gonna tell you about releasing code. I also hurt my finger, so I can't triple scroll back and forth, so I'm not gonna full screen um, sharing. But hopefully that is okay. So yeah, this is one of my favorite lessons of the workshop. We're going to teach you how to make your code able to be released publicly. So basically, you're going to learn by the end of this lesson how to make it pip installable. As always, we'll take a minute to appreciate the meme. This is basically the essence of making your code pip installable, is just figuring out what code you need to write and then taking it from other places that have figured it out already. Before we get started, I also just wanted to remind you all that you belong here and that this stuff is hard, but it can be learned and that you're learning it. All right, so by the end of this lesson, the main goals are that you'll be able to state the purpose of pyproject.toml, init.py, license, and README files. You'll be able to package a Python project for broad distribution. And you'll also be able to make your code publicly available on PyPy. Just to give you a brief preview of what the activities are going to be after the little intro to this lesson. First, you're going to create these additional files that you need for your repository, pyproject.toml and init.py. You're then going to package and upload your code to PyPy using Twine. You can follow specific instructions for that at this link. Then release your code publicly on GitHub. Create a Zenodo DOI for your package to make it citable, and then optionally add badges to your README file. I also want to encourage everybody to do a release today of your code, no matter what, your project code. People often want to wait until their code is like ready in order to release it. But it's really, it's pretty low stakes. Even if you anticipate that you're going to have thousands of users in the future, you can release like a version 0.0.1 and wait until you have like a first minimal working version to call that one v1.0.0. But it's really common to release like pre-release versions and put them on PyPy. So we encourage you to do this. It's important to practice the process of actually packaging and releasing. Okay, with all that said, let's do a little bit of motivation about why we might want to release code. After all, at this point in the workshop, you already know how to put things on GitHub, you know how to clone things to your local machine, and you also know how to do things like run pip install -e in a particular repository. So the secret is that under the hood, this pip install -e is calling a script that the author of that code has written to give them control over how the code is set up on your machine. Another reason to release code is that it gives you a really easy way to do version updating, especially when you have lots of users distributed across lots of different platforms and stuff. And it also makes it easy for users to install and use packages. Nowadays in astronomy, pip installing is a pretty widely accepted standard for open source packages. And people often expect your code to be pip installable if they want to use it broadly. All right, so let's go over some vocabulary. A package is anything that's installable. Package is package-related code together in one place. So you might see something like at the top of when you're importing code to say like import orbitize.utils. This dotted naming scheme prevents you from worrying about like conflicting naming conventions in other packages. So if you ever coded in like R, for example, there's actually not this initial like package name when you import things. So it's really easy for like, if Orbitize has a utils module and Radvel also has a utils module, you can't necessarily keep those two things separate easily when you import them in R. So this is a nice thing that Python does to keep the namespace clean. So modules are another level down from this overall package, like the umbrella of a package. A module in Python is any individual Python file is called a module when it's in the context of a package. And then a package itself is a collection of any Python files. The thing that actually defines a Python package as a package is that it has this special init.py file at the root. So if we were to make a flow chart of all of the sort of building blocks of packages in Python from the least information to the most information, you go from the smallest amount of information, which is just variables, to functions and classes, which are collections of variables and often do things. Then you have modules, which are maybe a given module will have several functions and classes defined inside of it. And then a package is several modules. So going back here, Orbitize would be the package here if you import orbitize.utils, and then utils would be the module. So whenever I learn about a new type in Python, generally the first thing I want to do is open IPython or a Jupyter Notebook and have it actually print out the type. And one very confusing thing that confused me when I started thinking about this is that Python treats both packages and module as type module. So if you're to import Orbitize, which itself is a package that has many files or many modules, and then you just print out the type, it will say that this is a module, even though the Python docs officially say that this is called a package. The actual thing that's a module, orbitize.kepler, for example, is also type module. If you want, this is sort of just a side note, but if you want more information about this, there's a nice link here. All right, so with that out of the way, let's start talking about how you organize files in a package. So this is an example from the Python docs about how a package might be organized in a sort of typical way. So generally you have the name of the package itself as a root directory. So this package might be called sound. If you wanted to import the whole package, you would just say import sound. Then there's an init.py within that root repository. So that's the thing that tells Python and setup.py, which we'll talk about later, that this is a package and that this can be installed. And then there are all of these sub-packages within the package that themselves each contain init.pys. And then each one of those might have a lot of individual Python files, which are called modules here. So if I wanted to import this particular module from the effects subpackage that is itself a subpackage of the sound package, I would type this in a Python window from sound.effects import echo. All right, so within this overall structure of a package, there's several different files that you need in order to make the package packageable and able to be installed on PyPy. So if you imagine this my package as at the root of the repository, so that's equivalent to sound here. There's a bunch of things that have to go in the root, and then the package itself, my package here, is the thing that will then contain all of your code files and the init.py. So this whole thing here on this previous slide is the equivalent of this. So generally, people are often confused when they see this type of file structure because you often say, oh my gosh, there's two things that people say this to me all the time, that there's like two orbitizes. There's an orbitize and then there's orbitize within an orbitize. This is super common. So the package itself will be the name of like the whole GitHub repository, and then all of the code files will live in a subfolder with the same name. Other common conventions are to call the subfolder like source, src. You might sometimes see other things, but those are probably the two most common. In this workshop, we're going to encourage you to have this like dual naming scheme where the root repository is named the name of the package. The root of the repository has the same name as the package overall. And then the subfolder where all of the files live is also called that same name. So remember, within this subpackage, within this subfolder, there needs to be an init.py file in order to tell Python that this is a thing that can be pip installed. So let's take a look at what init.py actually looks like. So an init.py lives in the same directory as your code files. It can be completely blank. You do need it, even though it can be completely blank, because again, it's the thing that signals to Python that this is a package that can be installed. But it functions sort of similarly to the init method of a Python class in that when you import the file, when you import the package, the commands in this file are executed. So let me give you a quick little demo of that. Let me share my whole screen, hold on. All right, so if I open up Orbitize, so here, first to give you a little tour, this is the whole Orbitize GitHub repo that I've cloned. So the root is called orbitize, and then you can see again there's this subfolder also called orbitize. So that's where all the code files live. And within this, there's this init.py, which is the thing, again, that communicates this is a package. So it's like,
Sarah, could you make it a little bigger?
yes, thank you. How's that?
How's that good? Better? Slightly bigger? A little bit more?
That's good.
Okay.
Okay, awesome, thanks. So yeah, so like I said, all the commands, this is basically just a Python file that gets executed when you import the package. So to prove that to you, I'll just add a simple statement. So let's say print hello, and I'll save it. And now if I go to this terminal down here, and I type IPython, I'll do import orbitize, and you can see it prints hello. So it's basically just executing everything in this init.py. If you don't have anything in here, then it won't do anything. It's very common for people to define like top level variables here. So for example, we're defining orbitize.datadir here, which is where we put data files that we want users to have for example use cases. All right, so that's init.py. The next thing I'm going to tell you about is pyproject.toml, which lives at the root of the repository. So that's one level up from where all of your code files are. This file specifies how your project will be built on a new machine, and it defines metadata about your project. This is actually a relatively new convention in like the Python scheme of things. So if you look at Code Astro recordings from a couple years ago, you'll notice that we don't mention pyproject.toml at all. And that's because it used to be a lot more common to use something called setup.py instead, which I'm going to talk about on the next slide. But yeah, so pretty much all you need for pyproject.toml to be functional is this. This is sort of the most minimal pyproject.toml script. At the top, this specifies like what program you're actually going to use to build your package. One of the most common choices is setup tools. So you can just copy this verbatim into your pyproject.toml. Then there's some metadata about your project. So you have a name and you have a version number. And then another important thing is your list of dependencies. So this is just a list of what would be strings in Python that specify all of the packages that you need to install in order for your package to run. And these will be like either checked that they're installed automatically either checked that when it's installing, it will check that they're installed. If they're not installed, it will install them automatically. So you all went through this when you pip installed Orbitize before the workshop. Many of you ran into issues with dependencies, for example. So it's because the pyproject.toml was actually specifying here are all the dependencies that I need to install, and then it'll go and install them or tell you that there's conflicts. One tip is generally to use underscores instead of dashes in your name of your package. Dashes in package names can lead to kind of annoying behavior, especially when you're dealing with docs. And it'll, often you can't, since dashes are not like a valid type of valid component of a variable name in Python, you can't import solid dash octo dash fish stick. So we recommend to just use underscores instead. This is a pretty common thing that people run into every year. All right, like I alluded to before, there are several packages in common use to specify how your Python package will be built. So pyproject.toml will be used no matter what actual backend framework you use. Setup tools is one way to do it, but you can also use pyproject.toml to use any other method that you might find out there. You actually can also use this now deprecated setup.py file in addition to pyproject.toml. And what I learned recently in trying to migrate Orbitize from setup.py to pyproject.toml is that pyproject.toml is pretty minimal, and it can't do a lot of sort of specific behaviors, install like more specific install things. So if you have like a sort of niche thing that you want to do when you're installing your package, you can have both of these files and then sort of code up your own things in Python and put those in setup.py and then just have the pyproject.toml in addition. If none of that made sense, don't worry. All you really need is pyproject.toml. I also made a minimal example of a working package that only uses pyproject.toml at solid octo fish stick. So if we copy and paste this, I can show you what this looks like. So you can see we've got the we're in the root repository, the root of the repository right now, which is called solid octo fish stick. And then the code files all live here in solid octo fish stick as well. This has an init.py. You can see it's totally blank. It doesn't have to have anything. It just needs to be there to communicate it's a package. And then we've got some very, very advanced code right here. And then I've also got a pyproject.toml at the base. So this is super minimal. You can basically just copy and paste this into your package verbatim, and then worry about additional modifications that you need to make as they come. All right, so next let's talk about the license and README files. So the README file is what users are going to see when they open your package on GitHub. So often people will write some documentation in there or include a link to their documentation page. So I'll show you what the Orbitize one looks like. So you can see readme.md, MD stands for Markdown, by the way, lives in the base of this repository. And then if you scroll down, you actually see the README here. So in our case, we've just got our logo, we've got like a very short description and a link to our documentation, and then a couple of badges. I really like badges. I think they're really fun. So encourage you to figure out. Well, I've got a link. If you want to add badges to your own repo, you can do that at the end. So the license is some legal mumbo jumbo that copyrights your open source code and gives you legal rights over your work. There's a handy link here to help you choose. So a couple things that I forget to mention every year and finally remembered to put in the slides this year is that critically, without a license, your code can't be used by other people. So creating a license makes it so that other people can legally use your work and adapt it. So really common licenses for astronomy code are BSD and MIT licenses. I've got a link here if you want to read about the differences between them, but I don't think it's super important to go over right now together. All right, the next file that I want to talk to you about is requirements.txt. So requirements.txt is a list of Python packages that your package needs to run. These are called dependencies. You might notice that actually a couple slides ago, I already indicated that in pyproject.toml, you have to specify your dependencies. So you might be confused why I'm telling you to have this additional thing called requirements.txt. This is mostly because requirements.txt is actually sort of a historical artifact at this point. It's gradually falling out of common use. And nowadays it's recommended to list dependencies directly in pyproject.toml rather than reading from requirements.txt. But that said, many packages still have their requirements separately in this requirements.txt file. And also other services often expect you to have requirements.txt. So for example, if you're doing an auto documentation builder, which we're going to learn about later today, one called read the docs, it will actually expect you to have a requirements.txt. So if you're not sure, it's probably a good idea to just list all of your dependencies in both cases. It's also totally fine to have different dependencies depending on what the use case is. So for example, you might need a particular version of Sphinx, which is an HTML builder for your documentation builder, but you might not necessarily need, you might not necessarily care about that for just like other users of your repository, people that are just going to download and install your code. So you can put separate requirements, separate dependencies in those two files, depending on what your needs are. All right, so that's basically it at this point. So once you've got all of those files, you can go ahead and test your installation locally. So the way you do this is you have all hopefully already done this with Orbitize. So you just change directory, you cd into the directory containing your pyproject.toml, and then you type pip install -e dot. So the -e here means that changes that you make to the code will be reflected on disk. So that means that basically if you modify the code afterward, you don't have to reinstall it. The installation on your computer will automatically get updated with all the changes that you made. So that's actually why I was able to, in this demo, in the init demo a couple minutes ago, I was able to make a change to the source code and not worry about reinstalling it. And then when I ran it, it actually automatically pulled from the version that I had on the disk. So if everything goes well, your package should be installed. And you can test it by just opening up an IPython window or whatever you usually use to just type scratch code and try to import your package. So you can now do this from any directory, not just the directory containing your package, because your package is actually installed on your computer. So it's sort of treated equivalently to like NumPy. So that's how to install your code on your own computer. Now the maybe best part of this is how do you then make your installable code publicly accessible so that other people can install it. So for this, we turn to something called PyPy. There's sort of three confusing terms that all come up when we start talking about this. PyPy, which stands for the Python Package Index, is a software repository tool for packages written by the Python community. Whereas pip, which amazingly stands for pip installs packages, is the package installer tool associated with PyPy. So you can think of pip sort of like Git, like it's a tool, it's a thing that does things, and PyPy sort of like GitHub, like it's a repository, it's a place where things are put. So you store your package on PyPy, you install it with pip. Conda, on the other hand, is a sort of more general purpose package management system. Generally, it's pretty difficult to get your code, I would say essentially impossible to get your code to be like accessible to be installed on Conda. So community developed tools like Orbitize are not installable with Conda. It's generally just installable with pip and hosted on PyPy. So how do you actually do this? I'll take a minute to appreciate the meme. This is another, what was the word? Rustic. This is another rustic meme. I think I made this one in 2020. So we recommend uploading each new version of your package to PyPy. So this is going to make your package installable from any computer, and it'll also make it able for users to install particular versions. So if you wanted to install like my package version 1.0, you just add this. It might be 1 = sign. I always forget what the syntax is. But you can install version 1.0. If you want to install version 1.4, you do it that way. Go away. All right, so if you want to make it so that your code is installable from any computer with this command, you need to upload it to PyPy. A really useful utility for uploading to PyPy is called Twine. So Twine itself is pip installable. So in order to do this upload process, you just run these couple of commands. This first one is going to make sure that you don't have anything currently in your like dist file, which is where the like distributable versions of the code go. So you make sure you don't have anything in there. You then pip install, build, and Twine, and then you build these packages. You build the package for distribution, and then the last step is to upload everything to PyPy. So that's it. That's the whole process. Some best practices that I want to go over. First is to also do a GitHub release every time you make a significant change to the main branch of your repository. So often if I want to release a new version of Orbitize, like I've made some significant change to the main code base, I will do a simultaneous GitHub release and release on PyPy. So best practices are to keep these consistent. One of the worst bugs I ever encountered was when the version of the code that I was looking at on GitHub was actually not the same as the version I had installed on my computer because the developer had not uploaded their most recent GitHub release to PyPy. So don't do that. Another best practice is to maintain a descriptive changelog. So this is something that will be readable by humans that goes over all of the differences between each individual change that you've made. So here's our example in Orbitize. This is just in our main docs page. If you scroll down a little bit, you can see we've got the version number, the date that the version was released, and a very quick overview of here's what we did. You can see the most recent thing that I did was changing from a setup.py install to a pyproject.toml install. And then we've also got who did the main work for each individual change. Yeah. And then you probably have also seen that there's this sort of 3-number system for releasing particular versions of your code. The crash course in this is that the first number you should increment when you make a very major functionality change, especially if you lose backwards compatibility, meaning that users, if someone wrote a script using your package with the old version, that script might not work with the new version of the code. So that's called loss of backwards compatibility. So for really big changes like that, incrementing the first major number is the way to go. For the second, you increment it if you make a minor functionality change. For example, if you add a new feature. And then the last one is for a bug fix. Sometimes I will also increment this for a documentation upgrade. Another best practice is to make your code citable. You can do this even if you don't have plans to publish a paper associated with your code. You can still accrue citations for your code, which is very handy in academia. So this is an overview of how to actually do this. I also want to show you what Orbitize's Zenodo actually looks like. So if we scroll down, I've got a badge to our Zenodo DOI. So if you just click on that here, then takes you, I guess it's linking to an older version, it then takes you to this Zenodo page. So first of all, you can see all of the authors of the code here, and then it also has binary versions of the code itself that you can download directly from here. It also archives every single version of the code. We've set it up to do this automatically, so every time I release a new version of the code on GitHub, it automatically creates a new Zenodo DOI and archives it on this website. And then another nice thing is that you can export the citation directly here. Sorry, one second. All right. Yeah, so the last thing I wanted to tell you about basically is publishing software papers. So even though I think it's worthwhile making your code open source, even if you don't plan to publish an associated paper, publishing a paper can be a good thing for your code. First of all, it's really good advertising. It makes the rest of the astronomy community aware that your code exists and what its functionality is. And it also gives people something else to cite when they use your code for their own work. That can be helpful for your own academic career. So I've given you some examples of software papers in astronomy here. These ones are a little bit older. They're not published in software-focused journals, but you can check them out for inspiration. And then another more modern option is publishing in the Journal of Open Source Software. Some nice things about JOS are that, first of all, there's a completely public review process. It's done completely on GitHub. So actually, the whole GitHub review is like listed within the issues of the GitHub page. And another nice thing is that not only the paper itself is reviewed, but also the code is reviewed. So the reviewer will actually like pip install your code and give you feedback on like anything from the structure of the code to like the clarity of the tutorials, etc. So a couple of examples. It's not in progress anymore. I can delete that. So, oops. I linked to the actual official JOS review for Orbitize v3 if you want to check out like what the review actually looked like. And then I also did I participated in the referee process for a different JOS paper, so you can see what that process looked like. JOS also nowadays has an option for you to submit jointly a AAS journals paper and a JOS paper, so you can submit the same paper to both journals and have your code reviewed and also the paper that's associated reviewed. All right. I also wanted everybody to be aware of our former TA, Paulina's excellent Jupyter notebook, taking you through the process of releasing your code. And also she's translated pretty much everything else in Code Astro into Spanish. So definitely check this out and let it also serve as inspiration for you to translate Code Astro materials into other languages as well. All right, so at this point, I'm going to release everyone to actually make your own code pip installable. So just to remind you about the activities, you're going to first create all of these extra Python files that you need for your package, then package and upload your code to PyPy using Twine, then follow this process to release your code on GitHub, and then make sure you have a consistent release on GitHub and on PyPy. Then finally create a Zenodo DOI for your package to make it citable. And then optionally, you could add badges to your README. We also have a badge specifically for like made at Code Astro. I should find the link to that and send it out too. All right, so I think we're gonna take 20 minutes now to do this. And then we will come back together and continue on from there. Everything good, Jason?
Yep, things are good. We're gonna break out.
All right, sounds good. I'll open the breakout rooms.
So we're gonna come back at 00, 40, 59.
Yeah, sounds good.
Sarah, you're still sharing screen.
Thanks.
Don't want to yes.
You can see my super secret messages with Jens.
Oh, breakout rooms, please.
Sorry, I forgot. I went through all the process except clicking the open button. See, they're open now.
All right, Dak.
It's the other thing. Yeah, it's really niche. That's why you use it. I mean, going on. So it's on the outside.
I don't know if they oh, I see. Yeah. You know that.
Oh, does it? That's great. It doesn't need to.
That's fine. Yeah. Well, no, actually.
It was like, we can move the other. Do we want to? And then put our names out, I think it's like. Probably. I guess. Also put out. Oh, I will. In the end, yeah, this is more so just like, making sure everything's okay. Yeah, that's kind of why I wanted to, like, I like it, it's, like, in the test, because this is really great. So I can make that real quick. I know I'm so excited. Oh, you just not that long? Yeah. Yes. How are you? Doing all right. A little sleepy. That's all. You were just saying, last day, how do you like that? Yeah. That's what I've heard as well, like, it's not all my friends. So she's like, there's nothing to do here. Yeah. Yeah, now I. Yeah. Where's you going? That was great. I'm getting this. Oh, like, when I saw that, I was like. Yeah, why not? So it's just like those things. It's just so. Yeah. I work early with, yeah. Yeah. There's like a lot of people.
Yeah, but
So like, I was. I grew up. Unfortunately, Yeah, I would argue with it. Very great. I would just. I graduated in, but I graduated recently. Oh, you. Yeah.
I have a very good.
Oh,
But it's a different one. Yeah. Yeah.
What's your name? Yeah. What's your name? Joe.
And I'm in Salesforce. I'm in my director. And I do, I thought. It like. AI took all the things closed and open again. A banana, not open, banana, that's.
Yeah, so this is right. Oh my god, I swear with that. Yeah. I would. I just.
I don't know why, it's also not something like that, actually, I like, yeah. I know,
Yes,
that right now.
Yeah. Yeah.
But I guess I'm just like. And, yeah, I'm not like. Yes. I'd love to try it. Okay, no, so I mean,
It's like in the process, it's working, it's working. Yeah.
well,
Yeah, I mean,
yeah, so I. Yeah, I don't.
I love it. I love it. Definitely very interesting.
Yes. That's fine, but this might come to you. I'm sorry. Yes, it's cool. Let's go. Share the scene.
The movie. Well, they split each act into its own, which I think order. I've also I've never actually seen these little side. Yeah. We're making it close to the end. So like, I think we're.
They did.
It could be okay. Like. So how do you?
Yeah.
Yeah, totally. Go to. Or should we say, as where that guy's going Please don't do that. I'm creating. And I said,
That's funny, but
this is really funny. I don't know what. I'm surprised.
So let's go back and figure out the bill dates.
Well, okay, so. The slices by, wait, okay. Right, and something, over actually going. I was thinking,
And should be available. So I would think so. So I think if I do this all, speak to the comment. So what is it? It's oh, nothing. You should, I don't have, oh, we really need to come out today. Yeah. So, but it's incentive, so.
Well, this is just, well. It's been too bad. Oh, that's. And then on.
Thank you.
Okay, let's wrap up in the next minutes and then
I think just be ecstatic, have this, and then whatever you input.
all right, everyone. Just to bring it back in for a quick bit, hopefully everyone got started packaging up your packages. You'll have plenty of time today to keep working on it. But let's take a 10-minute break here, and then we're going to talk about documentation, and then you'll have some work time on both documentation and if you want to come back, also packaging for your package as well. Okay, so let's take a 10-minute break. We'll return at 15 minutes after the hour. Okay, everyone, let's get back started. Um, we'll have another lecture on documentation, and then the rest of the morning is like basically for you to work on both aspects of first documentation, and then if you want to get back to your releasing your package, you can do that as well. Basically, kind of makes up for a missing afternoon work session. Okay, so we're gonna talk about documentation. Let me share my screen. Okay, I'm gonna hide meeting controls because I need to see the whole screen. All right, so we're gonna talk about documentation. So we'll take a second to appreciate the meme, our vintage memes. This one was made by one of the our original instructors, BJ Fulton, and who originally made this documentation lecture. But I have changed it this year for a little bit, and this is the first year that you're going to have a new part of this lection, which we're starting off with, called. Oh, actually, before we do that, first, yeah, documentation comes in many forms. Documentation can be inline comments in your code. Documentations can be doc strings. If you haven't heard about what that is, we'll talk about that in just a second. Documentation can be README files. These are text files that come with the code that's like, here, read this text file first before you do anything. And then documentation pages, such as web pages of documentation. Maybe you use a popular package that has a whole website that you can use that references how to install it, how to use it, and like how to call the function and things like that. Before we get started on like Python specific documentation, I decided to kick off with this new part of the lecture called Jason's hot takes on documentation. Right. Um, my view is that we as astronomers always feel like our code is not that well documented, and we're like, oh, we need to make our documentation better. And I think that that's not actually true. I think we only need a document code to be good enough, and we don't need to be perfect. And we only need to document it to the degree that it is needed. And like I said, these are hot takes, right? They're supposed to be a little bit controversial. And even especially sometimes if you actually go look, and actually I'll go to that in a second. Okay, perfect is the enemy of good. I think there are three most important aspects of your code to document if you document nothing else. You're like, I don't have time to do anything else. I just want to do the bare minimum. Like the bare minimum documentation that I think that you should do. First, how to install or set up your code. Just basically like, how do I install? You see from the code Astro repo, it's just like, run these lines of these commands. And the best thing to do, the optimal thing to do is literally list a series of commands that someone can kind of blindly copy and paste, and it'll work. And this is why we recommend having things like your PyProject.toml, getting it set up with pip and all of these things. So then instead of having to do this with a sequence of complicated Python commands, you use kind of very standard command line features that everyone is accustomed to, like doing, pip install your package, and everyone's like, oh, I understand how to do that. This is something that is pretty easy to do. And then one line usually works, and then your package is installed. So having a brief series of commands that I can blindly copy and paste is very good for how to set up and install your package. The second important thing that you should document is how to run your code for the most standard use case. Like I'm sure people, especially as astronomers, we often like find a package and we're like, how about what if we try to use this tool for this completely other thing that wasn't the original intent of the tool? Or how do I use this thing in this very specific way for my own research? This is true, but I think for any person that wants to get into a code, the most important thing to document is just how to run the code for the most standard use case. It may not be the one that they intended to use it for, but at least it shows them how the code can run and that the code does run. It's an existence proof that your code works. And the optimal thing to do is, again, a series of commands I can blindly copy and paste to get the answer. This could be a bunch of commands in a README file. This could be a Jupyter notebook that I can hit Shift Enter repeatedly until I get all the results. Something that's it's just an example that showcases the kind of primary feature of the package. And it's also great if you can document especially for astronomy, document the expected input output with units. Like if you're producing a number, if you're producing an image, if you're producing anything, what does the x-axis mean? What does the y-axis mean? What is the units of the number? Those are important aspects. But that's it. I find people are very resourceful in diving into other people's code and adapting it for their own personal use case. So you don't have to worry about accounting for all those use cases if you don't have the time to handle all that. If this is just this is not the thing you're spending all your time on. You at least should have a single use case that works, and then you can have some belief, have some faith in your colleagues that they will be able to adapt it for their use cases if they really want to. And then the third most important thing is how to cite your code. You should have some way to receive recognition for your work. So put that in somewhere that's obvious. If you use this software, cite X, make it pretty straightforward. Cite my Zenodo, you can cite your Zenodo DOI, as Sarah mentioned, you can cite a software paper you wrote. You can even cite a science paper that you wrote that referenced the software in that science paper. So whatever way you prefer, just have some ways that someone can give you recognition for that code in a very easy place. So those are the three most important aspects of documentation, in my opinion. This is the fourth. Oh no, we're not doing this. We're not doing this. We're not changing this live. Okay, get out of here. I'm not doing this. Okay. The fourth most aspect to document your code is document your code's API, or application programming interface. That's what API stands for. An API specifies what are the inputs of your code and what are the outputs. And we'll talk about doc strings. Doc strings are a great way to document the API of your code. Oftentimes, I don't need to know what happens in the black box function that happens underneath. Maybe you have a very complex algorithm. Maybe there's a lot of stuff going on. That's probably not the first thing I want to dive into. I just want to see how can I use the functions you've already written in a way that's useful for me. And to do that, I want to know how to call your functions, what are the inputs of your functions, what are the outputs of functions, and what does this function do, and try to reason if I can use that function for my use case. So those are probably the most important aspects of documentation of your code. The first three, I think, you can do without anything. You can put that in a README, you can put that in a text file, you can put that in a Jupyter notebook. You don't have to have very fancy documentation. Once we start talking about API documentation, things can get fancier and fancier, and we'll show you some ways to do API documentation and also building documentation pages from your API documentation. But that's like a next level of effort, basically, beyond like having a single README file or having a Jupyter notebook that describes your package and how to use it. And this is my favorite hottest take. Inline comments are not important. Yes, this is my hottest take. They have their place for explaining things like confusing parts of your code. But if you have an inline comment, it's like, now we're going to loop over all of the items in this list. And then the next line is for item in list. I think I can understand that. And this is something that in software engineering is called soft documenting code. So like you want to write your code in a clear enough way that it can be quote unquote self-documenting. And that's like the holy grail. It's like you write the code clear enough that someone reads your code and can understand from the code what the code is doing, the intention of the code, without having to read the comments. So, and you can actually, if you go to big open source software projects that's run by big software companies, like go to TensorFlow, that's written by Google, and like open one of their Python files, you'll see that there's actually not that many comments in their code, not many inline comments. You'll see that the API documentation, these doc strings, are well written, but there's actually not very many inline comments. And the goal of that is that the inline comments can actually are not necessary if you can write your code clear enough. And part of that is using things like descriptive variable names, and part of that is trying to keep your code short and simple. So if you're running a big complex operation in a single line, consider breaking that into multi-line steps so it's easier to read. Things like that, code clarity is part of code documentation in a way, and that can often replace inline comments. So, these are my hot takes on documentation. You can use them however much you want, but this is what I think are the most important aspects to document and what are the least important aspects to document for your code. Okay, so for the rest of this lecture, we're going to talk a little bit about various ways of how to document. And the first thing we're going to talk about are these things called doc strings. A doc string is basically a string, a series of characters, basically a bunch of words that appear at the beginning of a function or class that provides an overview for its purpose. It provides an overview for its purpose, a description of the input variables it expects, and the explanation of the output variables produced. Um, there are several different common styles for Python doc strings. I prefer generally to use the Google style doc string. There's also something like a NumPy style doc string, but I find the Google style doc string to be the easiest to read, which is why I prefer using that one. Here is an example of a function written with a Google style doc string. So this function name is called crosscore, and the inputs are just A and B. So you can see the first part of the doc string, it's just a couple lines, not really the most you want is a paragraph, but usually this is like 2 to 3 sentences at most. Oftentimes it's like one sentence when I write these doc strings. It's just a description of the function. It's a short summary, followed by a small block of text with more details about what this function does. So someone should be able to read this function, maybe a somewhat expert in this, but someone to be able to read this function and understand what is the purpose of this function without having to read the actual implementation of that function. So this function crosscore is a cross correlation function. It calculates the cross correlation of array B against array A. So cross correlation is a mathematical operation, and we're just multiplying or basically applying this mathematical operation between array A and array B. The next part of a doc string is the definition of the input variables. So this is very specific in Google style doc string. You always start out with this thing called args colon and then new line. So that tells you we're beginning the chunk where we're writing the input variables. And then each input variable is one indent in. And each the format is always as follows. You write the name of that input variable. So if you named it A here, it's A here. If you named it B here, it's B here. And then it's parentheses, it's type. This is the expected type that you expected to pass in. Python is not what's called a strongly typed language. That means that like A doesn't have to be an array. It could be a list, it could be an integer, and Python will let you pass it in even if the code crashes. But here you can at least give a hint, give an expectation for what kind of type you expect to be passed in. If you can expect multiple types, you can write multiple types here. You can be like int or float or array or list, if you're very flexible. Or if you're very specific, you're like, this is only an array. And then so it's your variable name, parentheses type, colon, and then the rest you can basically write as many lines as you want. Generally try to write only a couple sentences at most, basically a description of that variable name. So here, this is a NumPy vector reference against which cross correlation is calculated. And then B, NumPy vector, the resulting cross correlation function will show how B should be shifted to line up with vector A. So that's basically how you would document your inputs. And then Python always, when you can also document your outputs so that you do that with the returns colon section. And here, instead of you don't name, one of the things to note here is you don't provide the name of the output variable. So like you might have an internal variable in your function that's what you're returning, but as the user of that function, I don't care about that return variable because I never get to see it. So what I just care about is what is being returned. What is being returned here is a single array, which is the cross correlation function. So instead of having variable name colon, variable name parentheses array colon, here we just have instead of having variable name parentheses data type colon, we just have data type colon. So if this was a float, it'd be float colon. If this was an int, it'd be int colon. If this was a string, it'd be string colon. If this is your class that you made, it'd be the name of your class colon. And then a description of the output variable. Also a good place to put things like units, dimensions, things like that, just help the user know what to expect. So this is an example of a docstring for a typical function. If you want to see other ones, if you just Google Google style Python docstrings, this is like one of the first results on Google. And it basically gives you a whole list of example docstrings for different kinds of uh, docstrings for different things. You can have a docstring for a function like we just saw. Um, we can also have docstrings for classes. So here is a docstring for it's a little too big. Here's a docstring for a class. So here, the class docstring is relatively similar. At the beginning, you have like a one-liner for the description of the class. You have maybe a little bit more block of text for a more detailed description of that class. And then you have the args. This is how you create the class. So the class needs to pass in, and so this is basically what gets passed into the init function. So the init function MSG has arguments MSG and code, message and code. Message is a string, code is a string, code is an object, um, and it basically gives you a description of each. And in addition, a class doesn't return anything, but a class does have attributes. You can have state of that class that you're tracking. So here, the attributes, the public attributes of the class, the attributes of the class that you want other people to access can also be listed here. So you have attributes colon, just like arguments colon, attributes colon, and it's the same format as the arguments. Here we have a message string and a code integer that basically shows each of these. Um, Well, there's one like kind of confusing thing. Here in the init function, no longer has a docstring because basically the init function is documented in the class docstring. Some people like this, some people don't like this. You can also, and as a valid version of the Google style syntax, is to basically put your init docstring actually in the init function. So if you prefer this, you can put the initialization docstring here. This is how you actually, and instead of having the args up here for how you create the class, you would have the args down here for how you create the class. And the class docstring only has the description of the class and its attributes. The args of how you create the class the first time end up in the init function. Both are valid ways of doing Google style docstrings. Some people prefer one, some people prefer the other. But yeah, this is a nice page with a reference for a bunch of different examples for how the Google style docstring is used. Okay. And we write this in a very specific format because we'll show you in a second, we can actually generate web pages of API docs automatically in very nice, pretty formatting if you follow this syntax to a T. So we'll show that in a second. We'll use something called AutoDoc to basically generate API documentation pages from all the doc strings you write. So this is nice that you write the doc strings once, and then you don't have to go back and rewrite them again for your documentation web page. It will be built automatically. Here, I just wanted to make a brief detour to talk about this thing called Python type hinting. Like I said, in Python, by default, you can pass in any arguments, any type of argument into anything, and Python won't complain. Your code might crash, but Python won't complain. In other languages, if you try to pass in, let's say, a string to a function that only expects an integer, like that language will crash at function call because it's like you can't pass in a string to a function that expects an integer. Python will allow that, and maybe your code will crash, but Python will allow it. One thing, this sometimes is confusing and sometimes makes it a little bit difficult to kind of track, what are the types that I should be passing in. So in Python function definitions or class definitions, you can do something called type hinting. Type hinting is basically, instead of showing here cross correlation parentheses A comma B, you can do cross correlation A colon the expected type of A, B colon the expected type of B, arrow the expected output of the function. This doesn't do maybe doesn't do exactly what you think it does. It doesn't do this doesn't change the behavior of function. Python will still not check whether A and B are NumPy arrays and still will not check if your output is a NumPy array. So this doesn't like guarantee anything. It just makes that's why it's called type hinting. There are ways to guarantee it, but it kind of it requires extra decorators and things like that that we're not going into. But um, just doing this type hinting is useful in some ways. It helps code clarity. And it also makes it easier for IDEs and debuggers to identify bugs in your code. Just like how we showed that static linting in the first day, where if you mistype your variable, it's an undefined variable name. It makes a little yellow squiggly under it, being like this variable is not defined. If your IDE knows that this variable was defined to be an int, and you try to pass it into this function, and this function had type hinted that this argument should be a NumPy array, it will actually be able to identify that, hey, you're trying to pass in a NumPy array to a function, you're trying to pass in an int to a function that expects a NumPy array. This perhaps won't work. So a type hinting is useful for code clarity and to help it make it easier for IDEs to identify bugs in your code before you run it. So this is something you can do for your functions, but it's not not required, but it's something that could help with code clarity. Okay, so that's documentation for kind of at the code level. We're not going, like I said, we're not going to talk about inline comments because my hot take is inline comments are overrated. So those are how do you do comments at a function level or a class level. And I encourage you to get in the habit of writing doc strings for any function or class you write. It's basically like second nature to me now. I like define like def function colon, and then the next thing I do is type triple quotation marks basically to say something. It's a useful habit to get into. The next part of the lesson, we're going to show you how to make a documentation website. So a documentation website is basically a place where you can place all of your stuff. You could place it in a README, you could place it in a Jupyter notebook. Those are totally fine. But if you want something that's a little bit more flexible, can be more detailed, have many different pages, not just one single page. A document website is a nice thing to have. And we're going to use something that's pretty commonly used for Python development, which is called Sphinx. Sphinx is a way to build documentation sites. Sphinx doesn't necessarily have to be related to Python. You can have Sphinx documentation sites for other languages. This happens that Python is very popular. Sphinx is very popular for Python. So I'm going to show you how to make a website, a Sphinx documentation website with an example package. In past years, we've also tried to make this a follow along in type 1, but we generally find that follow on type 1s follow on typing doesn't usually work super well. So mainly I would encourage you just to watch what I'm doing and then you can do it yourself. We'll have plenty of time for you to do it yourself for your own package. So you don't have to do it for our example package. You can do it for your own package. So we're just gonna follow along. So in our day 3 code Astro, we've actually made a very, very tiny fake package. So inside of day 3, inside of tutorial doc, there is a package called correlate. Correlate is extremely tiny. Correlate has only 2 things. It has in a init.py, just like we saw Sarah talk about, init.py makes this folder a package. And then we have this function called correlate.py. And correlate.py has a couple of functions. You already saw cross correlation as one of the functions. And then it has a bunch of code. This one has a lot of inline documentation. And then it has maybe another function. And that's about it, basically. So we're just going to document basically 2 functions in correlate.py. So how do we do that? So you can kind of think of correlate as your package, basically. If this was a proper package, we should have in addition to our README, we'd have a license, we have a PyProject.toml, all those things would go over here, basically. Okay, so let's do this. So the first thing we're going to do is to make a docs directory in our repo. So we're going to follow along as I type. Why did this pop up again? Hide floating meeting controls. Okay, so we need to get out of day 2. We need to go into day 3. And then we're going to go into tutorial doc. So tutorial, where I am right now is like where you would be when you CD into the Git repository you just cloned. So like I said, there should be like a set of that PyProject.toml here. There should be a license file here, but we haven't had any of that. It's very bare bones. But what we'll do is we're gonna make a documentation dir, and this is something you'll do too as well. You'll make a separate dir that's documentation, and this documentation directory will live parallel in the same level as correlate. So your package is here, your documentation is right next to it. And it's all living, and if you had a PyProject.toml, it would also be here. If you had a license, it would also be here. These are all parts of things that is tracked by your Git repository. These are all things that would go into your Git repository. So I will cd into the documentations directory. I'm just following here. And then I'm going to run this thing called Sphinx quick start. And running this will basically make a very basic skeleton documentation, Sphinx documentation site for you. And hopefully this doesn't take too long. It's going to ask us a few questions. There we go. It's going to ask us if we want separate source and build directories, and the default is no, so we'll just keep it that way. Doesn't matter too much. You need a project name. We're going to call our project Correlate. You can call your project whatever you like. You need a project author. We're going to call our project author is code Astro. Project release. This could be your version number, version 0.1. Project language is ours is in English, and it'll have made something. So now if I ls the documentation directory, you'll see that it is no longer empty. It has a bunch of stuff. It has this thing called a makefile. It has these other folders. It has a conf.py, index.rst. We'll get into all of these in just a second. So the first thing we're going to do is open up conf.py in VS Code or another editor. This is the configuration file for the Sphinx builder. So we're here. We're going to open up docs. We're going to open up conf.py. So this is what conf.py looks like. Conf.py kind of has the metadata for your documentation site. You have things like we saw we just inputted. Our project name is Correlate, and it has inputted that. Our author was code Astro. We put that. Our version was 0.1. This is all stuff we inputted that ended up being propagated here. And it has some other kind of placeholder skeleton code that we haven't really defined yet. So let's see what the next step is. So the first thing we need to tell Sphinx is where to find your Python file. Sphinx doesn't know by default where does your source code lives. So to do that, in conf.py, we have to tell Sphinx where our code is. So if we copy and paste this to the top of our configuration, right, so we need to change it. So right now, conf.py is, this conf.py is here. Conf.py is in my code Astro day 3 tutorial docs. And we want to find out, we want to tell it where our correlate package is. Our correlate package lives one level down and in the correlate folder. So if I do an ls ... comma correlate, sorry, slash correlate, that's where our correlate stuff is. So I just need to go down one level and go into the correlate folder. This should be the same for you as well. For if you put your docs and your package with your init.py at the same level, you just have to go ... and then into your package name. This is one of the important parts of doing this correctly. So that's why we're taking quite a long time to explain it. Okay, so import OS, import sys, and then insert ... slash correlate. So if this was your package, you'd be ... slash whatever your package name was. Okay. Yes, building the documentation, I'll just say for every aspect you'll see this, building the documentation is rather finicky. you'll find, and that small syntax errors can basically lead to your docs completely breaking, and you're just like, what is happening? So getting the right pass is definitely one of those most finicky things, but be patient and ask us for help if you get stuck. But this is one of those things where it's just really finicky. And we try our best, but this is something that we run into all the time. Um, you can also make some additional changes to your conf.py file. We can add this line root doc equals to index. This defines that the root page, like the main page of your documentation, should be index.rst. So where's our author? Let's do that. Let's just follow it blindly. Root docs equals to index. The next step is to add Sphinx extension autodoc and Sphinx extension Napoleon to the extensions list in conf.py. So what are these things? Sphinx autodoc is an extension that allows us to build automatic documentation pages from our doc strings. The whole thing of like, let's spend all this time building nice doc strings. The autodoc extension will allow us to automatically generate documentation pages based on those nice doc strings. What is Napoleon? Napoleon is just Napoleon is what allows Sphinx to understand Google style doc strings, the particular doc strings that we are using. So we're going to put both of these in the extensions list here. And if you didn't install these, you'll need to pip install these two things if you haven't installed them. But they should have been part of the Code Astro installation instructions. And then you can also change your HTML theme. There's like many Sphinx HTML template themes out there. We're going to use the one called the Read the Docs format Sphinx RTD theme. This is one of the kind of standard themes that is used commonly in documentation pages. So we're going to use this one. And I'm going to do that by, I've already forgotten. I don't want to mess this up. Okay, HTML theme equals Sphinx RTD theme. Thank you, Matt, for doing this. There it is. Okay, good. You can see it. This is requires precision copy and pasting. Okay, so we're just going to make those changes just to kind of make sure our indexes are the default, to enable auto documentation of our doc strings, and then to change our HTML theme to this one that is kind of very commonly used for reader docs. Okay, so we haven't done anything. We actually haven't documented any of our code. We just want to make sure that this works. So this is not going to produce any real documentation, but it will produce an output. So we're going to do make HTML. And this will take maybe 30 seconds to a minute to run, but this will generate all your HTML pages. Oh man, no theme, Sphinx RTD theme. This is I swear I tested this morning. Okay, let's see. If this doesn't work, we're just gonna revert the theme. Okay, I guess I didn't install it. I have no excuse. Okay. We'll wait until I install this. But basically, we're gonna make a package, and that package, we're gonna make a bunch of HTML pages, and they're gonna end up in this build folder. And hopefully it's gonna work after we do this. Take 1 second. Right. Make HTML. Try to. Yes. All right. I was scared that the live demo was gonna die. Okay. Now in the build folder, you'll have a folder called HTML, and those will be web pages that we've automatically generated. So in particular, we've generated one called index.html. So let's open this one. I don't like I just opened it up in a browser. So how do I do that? Review, open file, export. Index.html. Wow, we've made correlates documentation. Currently it has nothing. It just has welcome to correlate documentation and an index which is currently totally empty. But we've at least have a site. We can fill it up with whatever you want. You can fill it up with installation instructions, you can fill it up with how to run your, excuse me, how to run your code, all of that stuff. We're And there's a bunch of, if you look up Sphinx kind of documentation tutorial, you can, or restructured text, which is the type of file format that Sphinx uses. You can look up how to basically write whatever you want. And we're not going to show you how to like write an installation page or things like that. The best way to do that, as Sarah showed you in the previous Python releasing packages side, is to steal it from another web documentation page that you like. You go like all the documentation pages for all your popular favorite packages are part of their GitHub repository. So go into their docs folder, look at how they wrote their documentation page, and you can steal as much of it as you want. Okay, copy, not copy. Base your documentation page off of it. Okay, all right. What we will show you today during the demo is how to do generate automatic documentation for API. So there's nothing here. So what we want to do is make a API documentation page for the correlate package, for the correlate module, sorry, for the correlate module. You make it for a module at a time. So here I'm going to go into my source code. So all my source code lives in, confuse myself. Yeah, so if I go into my docs folder, at the base level of my docs folder, there is an index.rst. That's my default landing page. I can make other pages as well. So I'm gonna make a correlate.rst page. So I'm gonna make a new file, correlate.rst. So this is a new restructured RST is restructured text. It's a very specific formatting style. But there's guides online for how to use that particular formatting style. So we are going to copy and paste this, and I'll talk about what this should look like oh, nice. We're going to copy and paste this, and then we're going to describe what this does. So when we copy and pasted all of this, what does this all mean? This dot space underscore correlation colon is the name, it's the label of the page. If you guys use LaTeX and know like about figure labels and things like that, this is the equivalent of that. This is how to get other restructured text pages to reference this page. So this is just the name, the label of the page. It has nothing, it doesn't do anything with the actual visual of the page. It's just the label of the page for the program. Correlation functions, this is the title of the documentation page. This will become the big title. It also become the title in like the little nav bar on your Internet Explorer browser. And then the title is always followed by a bunch of equal signs like this. This is what tells restructured text that the line above is the title. So the combination of these two lines indicates that this is the title. You can put any arbitrary text anywhere you want. So if you just start typing, this is just additional text that will appear on your documentation page. And then this very specific set of commands is the auto doc extension that we said we put in the extensions. This space auto module colon space correlate tells us to look at correlate.py in the correlate folder with the init.py that we set. And the members colon tells us to automatically parse every doc string in that Python file and put that doc string here. The next thing we want to do is that we've made a web page, but it's just kind of off in the ether. Our landing page is index.rst, so we want to link correlate.rst to index.rst. So when someone goes to a landing page, they know that this is a page that exists. One of the things that we can use to do that in restructured text is just to put it in the what's called the talk tree table of contents tree. This basically tells you what are the other documentation pages that live on this page. So if you go to index.rst, which is an auto-generated page that we have not even opened so far, this is what it looks like. This is welcome to correlate documentation. That's exactly what you see here. I can type blah, 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 and that will appear here next time I build it. And underneath that, here, this is the talk tree. So if I put correlation into this talk tree, because, oh wait, sorry, not correlation, correlate.rst into this talk tree, then it will know that in addition to index.rst, I should also provide a link to correlate.rst from the main page. Okay, so let's see what happens. And this is the moment of truth that I got everything right. Make HTML. All right, let's see what happens. So I'm gonna go and refresh this page. And now we have our blah, 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 blah. And we have in our table of contents tree correlation functions. And then if we click on this, we have our API docs for the correlation page. So those doc strings that we wrote with those very specific formats, that args colon with the, in the variable name, parentheses, variable type, colon, gets formatted like this. The returns gets formatted like this. And all like the words in like at the very top of your documentation get formatted like this. So you get this very nice documentation page. It even you can link directly to each of these documentations. Yes. Anyways, it basically produces this very nice documentation page for all of your API. So putting in all that effort ahead of time allows us to do this with relative ease. Question? Yes. So the question is, are we able to edit this and use show examples? For one example is NumPy plus examples for how to use these functions in the API. There's two-ish answers. One is yes, kind of, and B is you actually end up needing to put a lot of this in your doc string. So the NumPy examples are actually in the NumPy functions doc strings. So if you actually go open the NumPy source code, all their examples are in there, written in restructured text format at the very bottom. But so you can't really modify what goes on in between these API, these particular API things. There might be ways, but it involves more complex usages of Autodoc than I actually know. But you can put things at the very top. Like before any of this stuff happens, you can write arbitrary text. So if I go correlation functions that perform correlations, blah, 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 and I do make HTML, that would appear. So you can edit code up here, but you can't really edit code in between here. So if you want to edit code in between here, you need to put it into the doc string. Question?
Your local machine hopefully and
Mhm.
so put this on GitHub or like make like a say or
Yeah, the question is this website still on a local machine and what happens after this? This is the next step. So So indeed, this is only a website that's built locally on your machine. For best practices, you should only commit the source code. You shouldn't commit the build directory into GitHub. Best practices is to only commit the source code to GitHub. So you will push the conf.py, the index.rsp, all the stuff here. But everything in these three folders, underscore templates, underscore static, and underscore build, you generally do not push to GitHub. And then we'll talk about at the very end of this lesson. Actually, I'll just talk about it now. And then we'll just basically give you free time to work on your project after this. Where is everything? Yes. So we'll talk about how to then move it to read the docs, to move it to a website that you could deploy. Another question. A question is, what about private functions? Do they get documented? I don't remember anymore. Private functions in Python are only a suggestion, just like how types are a suggestion. They just have an underscore in front of them. I think they may not get documented by default, but I don't remember the behavior. Yeah. Okay. Anything else? Let's check the chat. Yes, everything here can be edited. So like the conf.py, all the defaults that we put in are all here and can be edited. All of the, everything here is editable. So you don't have to worry about anything being your final answer when you first set up the documentation page. Okay, right. Let's wrap things up because this took longer than I thought. Okay, some tips and tricks for doc strings and restructured text formatting. Check out additional examples. Check out how other people did it. You can kind of copy what other people do is the best way to do some of these things. RST files have a lot more text formatting options than what's shown in the example. So there's a bunch of cheat sheets or various tutorials online for all the things you want to do. So if you want to look up, can my I want my documentation page to do blah, you can search and there probably is a way to do what you're looking for. Doc strings and RST files can be finicky regarding syntax and getting auto-doc working. So be patient, and this might take a little bit of work. So if it fails the first time, that's okay. That happens quite often. I'll let you guys read some of these on your own if you're interested. I think there are just details there are like syntax specifics on restructured text. The activity and the kind of the rest of the we'll kind of wrap up at like 55 minutes at the end of the end of the hour, but I'm going to cover one more thing before we get to this actually. Linking Sphinx, since this was asked, linking Sphinx documentation with read the docs. This is if you want to, you can. This is kind of beyond the scope of what we expect you to do even in this week. Is you can use this popular documentation hosting service called Read the Docs to make a website, a publicly hosted website for your Sphinx documentation. Read the Docs provides a nice tutorial for how to do this. You basically need a public GitHub repository and a Read the Docs account, and those are the only two things you need. The hard part is getting Read the Docs. Like you saw that I even ran into some errors in the live demo getting Read the Docs to build up my machine. You now have to get you have to get Sphinx built. You have to get your package installed and Sphinx built on a remote virtual machine that you have no control over. It is doable. It is sometimes very frustrating. Both Sarah and I have lost days sometimes to getting it built correctly when they change something and deprecate various things. But it is doable. For simple documentation pages, I believe you all should be able to do it. But we are putting it as something you can do, but is outside the scope of this workshop in the terms of we don't expect you to try to do this if you don't get to it. But it is, in theory, doable. I'll just say that. And other people from previous years have done it. So it's not like it's impossible. I'm just saying that you may run into issues and the issues may cause headache. So enter at your own peril. Okay, so for the rest of today, for the next 50 minutes, we'll wrap up in the last 5 minutes. For the next 50 minutes, let's work on building a Sphinx documentation for your own project. So you don't need to do it for the example project. Do it for your project you're working on. So get together with your groups. Try to document at least one function in your package with a doc string. And then use Sphinx documentation for your project repo. Build the docs pages and try to build an auto doc page for at least that one function you have a doc string with. Okay, questions? Yes.
Docs website that you just created, not be public with like the URL, in which case I drive on them.
So, so the question is that we just made an HTML page. Why can't that be public? Why do we have to use read the docs? The answer is yes, that can totally be public. It just every time you edit the page, you have to regenerate the page and redeploy it. So read the docs does that automatically. So every time you upload a new change to GitHub, a new update to your RST page, the read the docs, if it's correctly set up, will automatically recompile all your documentation and redeploy it with those updates. You could, in theory, just put those HTML pages we auto-generated into some random, any website that you're hosting, and it will display there. Totally fine. Users have to manually update it every time you generate the docs. Okay, so let's break here. We'll come back at 55 minutes at the end of the hour. I'm going to open up breakout rooms for folks on Zoom, and let's give it a go.
Yeah, it's
No, I'm sorry.
I actually remember starting to like. I like. I didn't like stop.
Yeah, yeah, yeah.
All right. Wait, okay. Let's just wrap up briefly. I heard a lot of successes, people making documentations or uploading their package to PyPy successfully. So great. Great job. I think this is always the most satisfying day. It's like you have all this stuff and it's coming together. So keep up the good work, everyone. I just wanted to mention one thing I forgot to mention on documentation. Um, here's a few things for kind of things to put into your documentation site. If you're building a Sphinx site or even building a README, consider putting things like installation instructions, quick start guides, tutorials, and code examples, how users can cite your code, like I mentioned. Also things like a change log. So every time you release a new version, maybe write a few bullet points for this is what changed in this version. What new features were added? Well, maybe are there breaking features? Like is a function deprecated? Is this function changed in some way? That way a user can quickly glance at it and be like, oh, this is something important I should be taking notice of. And also, how other people could contribute to your code or raise issues to your code. Like, do you prefer people to email you, put issues on GitHub, things like that? And how do those things happen? And so yeah, that's it for today. I hope everything is going well. Like I said, there's no more activities, no more optional lessons today, no more structured activities. For the in-person people, you're welcome to go to Sierra to hang out if you want. Otherwise, the afternoon is free. For the in-person folks, remember we have our workshop dinner at 6:30. Otherwise, we'll see everyone here tomorrow, back at 9 a.m. Central Time on Thursday for the final day of lessons before we get to before day 5's project show and tell. Okay, all right, let's wrap it up here. Thanks everyone, and thanks everyone on Zoom. Bye everyone.
Thank you.
Bye.
Yes, I'm going back to my house.
So, yeah, just give me